Calculus BC, lesson 3.2, differentiability. Keep getting more and more intricate here. We worked on creating a derivative last lesson. Now, there are some situations where a function can fail to have a derivative, so we need to look at those. The first one is what we call a corner, and that would be absolute value. So, is it a function? Yes. Is it continuous? Yes. Does it have a derivative? No. Why not? Well, just think about the slope here and the slope here, and I'll let you figure it out. Same idea on a cusp, which we've had a few of these examples out there. Looks something like this if you zoom in enough. I believe that'll be f of x equals x to the 2/3. Continuous, it's a function, all that good stuff, but it doesn't work. The derivative on both sides of the zero is different. Can you find the derivative here? Yeah, of course. But you cannot find the derivative at x equals 0. Now, one that always catches me off guard. Want to find the derivative at 0? You say, yeah, I can. It's getting, here's the tangent lines, getting more and more vertical so that at the 0, it's perfectly vertical. Well, then we can't find it because that would be undefined, and you can't find it undefined. You can't write down undefined. There is no derivative. That's a graph of the third root of x, x to the 1/3. And a discontinuity, which could be anything. We'll just put a GIF function in there. So that's an example of, well, we'll just do it manually. If x is less than 0, and if x is greater than or equal to 0. So, find all points in the domain of f of x's absolute value of quantity x minus 2 plus 3 where it's not differentiable. And by the way, what's the two possible values for the derivative? So you graph. That's why you spend all that time in pre-calc getting good at graphing. Even though you can use your calculator, it's got to be quicker. It's up 3, should be left, but instead inside goes to the right. The derivative over here will be 1. The derivative over here will be negative 1, because that's the slope of the line. No derivative at x equals 2. Because the two derivatives are coming together, and you don't know which one it is, 1 or negative 1. Can't draw a tangent at a point. So, a good way to think about differentiable functions is to say they are locally linear. And this is actually a fairly easy concept that really bothers people. So I draw some curve, and then we go in here, and we zoom, and then we zoom, and we keep zooming until that point when we zoom in really, really close, it looks like this. How close did we have to get to make it look like that? Depends. Apparently I can't draw a straight line. Wow. Can't draw a straight line. But as you get closer and closer, it looks linear. It looks like it's becoming a line, which is good because remember the derivative is just the slope. So we zoom in close enough, we can say, oh, there it is. Yeah, we'll approximate on either side of that point. As a matter of fact, we'll approximate 0.001 on either side of the point. Well, where do we get that number? I don't know, we just picked it. Why not? And we can say we'll use that above and below the point. So that's what this means. And it's called the numerical derivative, and you need to remember that phrase when I say take the numerical derivative, you know to do this. And it just means, here's our curve. We've been doing secants. We want to know at this point A what the derivative is. We say, listen, let's go really close up and above, up and below, and that's close enough to approximate it. And the 0.001 we've picked as random, but we've used it, it's been used so much through the years that they say, yeah, that usually gives us a pretty accurate representation. And this would be from this dot to the point to that dot, this distance right here to here is what we used to call h, but in this case we'll call it 0.001. Same thing for this distance in here. And that means that this point here is f of a plus 0.001 going out to the top green dot, and this is f of a minus 0.001. So again, it's just slope, change in y over change in x. All this fancy dots and lines and secants and tangents, it all comes back down to slope. So here's the good news. Your calculator will do this for you. We're going to do it right here with the calculator, and then I'll show you what it would be by hand. You can check it if you'd like. Pause the tape. But before we do that, what if we want the function in terms of letters, not numbers? Well, that's fine. NDER. I always feel stupid doing this because it doesn't really change. It just means plug in x wherever you had a. By the way, why are we dividing by 0.002? That's because there's two of these gaps up here. So it's 2h. So you just plug in x. If I say, hey, give me the function, I don't care what the actual derivative. I want to know what the function that is the derivative is. But it's nice because you can put it all on the calculator. So let's approximate what's going on at 2. So math 8. It says n deriv, and it doesn't pop up that way. It pops up with all this nonsense, which is a little hard to see. Take the derivative with respect to x. The function we're doing is x to the third. I'll confirm that. Yeah, x to the third. Scroll over, and we're checking at x equals 2. If we wanted the function, we just put in x equals x. Curious what would happen if we did that. And it approximates it for us, 12.00001. I think that's what it was. Don't really care. If we wanted to do it by hand, we would go 2.121 to the third minus 1.999 to the third over 0.002. And I said I wasn't going to do this, but I guess I lied because I think I'll try that. 2.001 to the third minus 1.999 to the third all over 0.002. And of course I got the completely wrong answer. Probably because I divided by the wrong thing. Let's see if I can copy this. Go in and change it. No, that's what I wrote. What I did wrong. Oh, I'll have to go sort that out later. So we'll have to use the original one up here at 12.001. Minus looks good. Figure it out later. So will this always work? Well, we can do this for absolute value. Math 8. Derivative with respect to x. Math over 1. absolute value of x, get me out of here, at 0. And it gives us 0. So n deriv but we just noticed on the previous page that we have a corner there. So there's no derivative. So watch out. Point of the mini aside here is that ender can lead us in the wrong place. Not a big deal. Let's graph with it. So natural log of x looks like this. And let's graph with it. So it's two ways to do this. Let's just do it this way. Natural log of x. And then math 8. Derivative with respect to x. Now I'm going to have a little fun here. Alpha, let me try this one. I think it's over there. Yeah, I can plug in y1, meaning natural log of x. I could also have plugged in natural log of x on my own, but I thought I'd be goofy there. And we put in x, so that it'll graph the function. It's not a specific point. We hit graph. There's our natural log. And there's our derivative in red. No derivative on the left side because natural log is not defined from 0 and below. So there's our derivative, there's our function, here's our derivative. And I happen to know that that's the function 1 over x, where x is greater than 0. So how do we get the other side? I wonder if we could try and play with that. No. Another time. Now, a little more theory stuff. I'll gloss over it. It's not hypercritical. Differentiability implies continuity. If I can take a derivative, it's continuous. However, being continuous does not guarantee differentiability. That's what we started with. Might have a corner that is continuous but not differentiable. Differentiability guarantees continuity. That's a theorem. Don't get hung up on it. And then the intermediate value theorem, which really gets hammered on in theory texts because you need it to do everything going forward. For us, we just make assumptions, generally speaking, and run with this. But here's the converse of the intermediate value theorem, where we say, does any function have the unit step function as its derivative? And we would look at the unit step function, something like this, I believe. Put in 1, we get out 1. Put in -1, we get out -1. And no, choose any a between -1 and 1. And we would say, oh, look, we don't get all of these values in here. And that's what the intermediate value theorem says. We'll have all those intermediate values, but we don't get them here. So no function has the unit step function as its derivative. More on this as we go along, just setting you up for the future. That's about it. Happy mathing.